You know when you double-click an icon on your screen? Have you ever stopped to wonder what's actually happening under the hood? How does a simple line of code turn into real action? Well, today, we're going deep inside the central processing unit to see how it literally eats instructions. I'm Dr. Sudheendra S G, and this is The Explainer.
So, here's what we're going to do. We're going to follow the complete life of one single instruction. We'll start with the classic old-school model, and then we're going to layer on all the incredible, mind-bending tricks that modern processors use to get the speeds we see today.
Okay, so first things first. Before anything can happen, your program has to get to a place where the CPU can actually see it. Your operating system takes care of this part, pulling the program's code and all the data it needs from your slower storage, like your SSD, and loading it directly into the much faster system memory, what we all know as RAM.
Right, so the program is now sitting in RAM. The CPU takes over. And you know, at its heart, the CPU's job is surprisingly simple. It's just a constant, repeating cycle of work.
This entire core cycle really just boils down to three fundamental steps: fetch, decode, and execute. That's it. The CPU just does this over and over and over again, millions and even billions of times every single second until your program is done.
So what do those steps actually involve? What does it mean to fetch or decode? Well, let's break down the anatomy of what the CPU is actually working on.
First up is fetch. The CPU has this special little pointer called the program counter, or PC for short, and its only job is to hold the memory address of the very next instruction it needs to run. The CPU sends that address over to RAM, and RAM sends back the ones and zeros of that instruction, which gets stored in another special spot inside the CPU called the instruction register.
Next up, decode. Now that the CPU has the instruction, its control unit needs to make sense of it all. It basically splits the instruction into two key parts. There's the opcode, which is the verb. It's the what to do, like add or load. And then there are the operands, which are the nouns, the who to do it to, like which piece of data or which memory address to use.
And finally, execute. This is where the work actually gets done. If the instruction was to add two numbers, the arithmetic logic unit, the ALU, does the math. If the instruction was to load data, the CPU goes and reads it from RAM. This is the action step, the part that really changes the state of your computer. Let's walk through a super quick example to see it in action. First, the CPU fetches and executes an instruction to load a number from memory location 14 into a spot we'll call register A. Then it does it again, loading the number from memory location 15 into register B. The next instruction is to add them, so now the value in register A becomes 17. And finally, it stores that result back into memory location 13. See? Simple, effective, just fetching, decoding, and executing, one after the other. Now that classic cycle is the foundation for everything, but let's be honest, it is nowhere near fast enough for the modern world. So now let's get into the really cool stuff, how CPUs manage to completely shatter that classic speed limit.
And that's a fair question, right? If the cycle works, why did we have to go and make it so much more complicated? What was the fundamental problem that engineers were trying to solve?
The problem, in one word, is speed. A massive speed difference. Your CPU is tearing along at gigahertz speeds. That's billions of cycles per second. But your RAM, it's just so much slower. A CPU waiting on RAM to deliver data is like a Formula One race car having to wait for a person on a bicycle to bring it fuel. It's a huge bottleneck.
So what was the first big solution? Caching. A cache is a small but extremely fast pocket of memory built right onto the CPU chip itself. Think of it like this. If RAM is a giant library across town, the cache is a small cart with all the books you need for your current project sitting right next to your desk. Getting what you need is almost instant because there's no long trip involved.
The next really big idea is called pipelining. See, instead of processing one instruction from start to finish before starting the next one, the CPU overlaps the stages. It works just like a factory assembly line. While one instruction is in the execute stage, the next instruction is being decoded, and a third one is being fetched, all at the exact same time. This massively increases how many instructions get finished over time.
But it doesn't stop there, not even close. Caching and pipelining were just the start. Modern CPUs use even more clever tricks to squeeze every last drop of performance out.
A pipeline is amazing when a program is just a straight line of code. But what happens when there's a choice? You know, an if statement. This is called a conditional jump. It's a fork in the road. If the pipeline is already full of instructions for the path you don't take, everything has to be thrown out, and that wastes a ton of precious time. The solution to this is it's brilliant. It's called branch prediction. The CPU literally makes an educated guess about which path the program is most likely to take, and it starts working on those instructions ahead of time. And here's the crazy part. Modern predictors get it right over 90% of the time. When they're right, the pipeline stays full and everything is fast. When they're wrong, it costs a little time, but the wins are so huge, it's totally worth it.
So then engineers thought, why stop at processing one instruction per cycle? A superscalar CPU has multiple execution units. So, for example, it might have several ALUs. This is just like a grocery store opening up multiple checkout lanes. By having hardware that can run in parallel, the CPU can execute several independent instructions at the exact same time in the same clock cycle.
And on top of that, designers started adding specialized hardware for really common tasks. Things like decoding a 4K video or encrypting data. They can be really slow if you just use general-purpose code. But if you build a dedicated piece of hardware just for that job, those operations can be done orders of magnitude faster.
And now, we get to scale everything we've talked about up to the final level, the modern multi-core processor that's sitting in your machine right now. What is a quad-core processor, really? Well, it's basically like having 4 complete, independent CPUs, each with its own cache and pipeline, all living on one chip. It's like a restaurant that has 4 separate kitchens instead of just one, all working on different orders at the same time. This is the heart of modern multitasking.
Okay, let's put it all together. Here's the full journey. The operating system loads the program into RAM. Caches start prefetching what the CPU will probably need next. The pipeline keeps a whole bunch of instructions in flight at once. The branch predictor guesses which way the code will go to keep that pipeline full. Superscalar units execute multiple instructions in parallel, and multiple cores run totally different streams of instructions all at the same time. It's a symphony of optimization.
So you see, feeding a modern CPU isn't a simple read and run process anymore. It's this incredibly complex dance of caches, pipelines, prediction, and parallelism, all working together to keep billions of instructions flowing every single second. So the next time you see a loading screen, you'll know it's not one thing happening slowly, but a symphony of billions of tiny operations firing in perfect harmony. Thanks for watching.